Hi, everyone. I'm Sean, co-founder and CTO at Cerebras. When we started Cerebras, we had a vision to drastically change the landscape of compute for AI. And the reason for that is that we believe compute enables AI to have a transformative impact, just as Sean just mentioned. And behind that is because compute is the path to higher model intelligence. Now, we all know this, and this is why we as a community have been creating better, higher quality, and more intelligent models year after year after year. Now, when we first started, this was easy. Make the model bigger, give it a lot more data, and most importantly, throw a lot more compute to train the model. And just like clockwork, the models just kept getting better and better. In fact, we even have scaling laws that predict this trend that the research community has published years ago. However, now we're seeing that pre-training scaling alone is insufficient. And it's not just because the amount of compute is becoming unsustainable, but we're running out of data. I'm going to quote Ilya Sutskever. He said, "We have but one internet." Right? We're running out of data. So pre-training scaling alone is not sufficient. To get to the next level of intelligence, we still need a lot more compute. But it's not just in training. We are now entering the age of inference-time compute. And guess what? It also follows its own scaling law. During inference, the more tokens you use, the higher the intelligence. And this has also been published by OpenAI and others in the research community last year. But if we take a more recent example, like the Qwen 3 model, this is a state-of-the-art open-source model that was released just a couple weeks ago. In this graph, we're showing scientific question and answer. It's a benchmark called GPQA. On the x-axis is the thinking budget. This is the amount of compute the model can use during inference time to think, measured in tokens. On the y-axis is the score on the benchmark. Higher is better, higher is more intelligence. Now you can see there is a very clear trend here. The more tokens you use, the higher the intelligence. Now, this is scientific question-answer, but this isn't unique to one benchmark. Here's coding. Here's math. The more tokens you use, the higher the intelligence. And this is very intuitive, right? We can all relate to this. Because I know if I answered a question with the first thing that came to my mind, I know I could come up with a more intelligent answer if I was allowed to think through the question before responding. And this is the reason these models are called reasoning models, because they can think and they can reason through their response before they answer. And today, every state-of-the-art model is a reasoning model. This is the intelligence index for all of the popular models out today. Purple is reasoning, blue is non-reasoning. And as you can see, all of the best models are reasoning models. In fact, what's remarkable is that even the worst reasoning model is better than the best standard non-reasoning model. Reasoning is the only way forward to achieve state-of-the-art intelligence. And this is the reason why all of the best models from all the top AI companies now are reasoning models. O3, O4 from OpenAI, Claude Extended from Anthropic, R1 from DeepSeek, they're all doing this. And this is amazing, because through inference-time compute, through reasoning, we now have a path to yet even higher quality, even more intelligent models. But we have one problem. Aran asked a question on Twitter a couple weeks ago. Aran, are you in the room today? All right, if you are, I just want to thank you for asking this question. He asked a very simple question. Why are so many people still using 4.0, which is the standard non-reasoning model, when 0.3, the reasoning, the more intelligent model exists? A very simple question. What do you think the answer is? The answer is also really simple. Speed. Quote, because I don't want to wait a year for a response. Reasoning models are too slow. The 0.3 model, which is the reasoning model, is, quote, slow as hell. There's even a snail emoji there. What we're seeing here is a direct consequence of that inference-time scaling law that we just saw. The more tokens you use, the higher the intelligence. More tokens equals higher intelligence. But we also know that from a practical standpoint, given a fixed time budget, faster inference equals more tokens. And almost like I'm giving a math proof here, through the property of transitivity, that means faster inference equals higher intelligence. This is our scaling law. This is what we strive to enable at Cerebras. And this makes perfect sense, right? Because if the model is too slow, you simply cannot access the intelligence. So let's dive a little bit deeper here to see what's going on. In your standard non-reasoning model, you give it a question, and the model takes maybe 1 to 2 seconds to process the question and starts to respond. We saw that in some of the videos earlier. On a reasoning model, however, you give it a question, and it actually thinks through the response before giving the answer. Now, during this time, it might be breaking down the problem, might be solving the individual parts, even verifying its own answers, maybe drafting a solution, revising it, so on, all before giving the answer. Now, that makes perfect sense. It's probably what you or I would do if we were given a question, right? But it's important to note that during this time, the model is just generating more tokens. All this thinking is just more output tokens. And this is why, for a reasoning model, given a question, it might take multiple minutes before it even starts to generate a response. And ultimately, this is the reason why these reasoning models often are impractical or simply irrelevant in many use cases, even on the fastest GPUs today. Now, why are GPUs so slow? The fundamental reason why GPUs are so slow is because AI models are measured in gigabytes in size, but the amount of on-chip memory on a GPU is measured in just megabytes. So that means that only a tiny little portion of the model can be stored on the on-chip memory of a GPU. Now, in the GPU architecture, the way you work around this is you store the model literally in a separate chip. This is HBM, right? If you didn't know this, HBM is actually a physically separate chip from the GPU, which is actually doing the compute. But when you do this, it means the model weights are now far away from the compute because they have to go through this tiny, narrow memory bus to be able to reach the compute. And this is the memory bandwidth bottleneck that limits all inference performance on GPUs today. Now, at Cerebras, we took a different approach. If you think about it, there's been many, many companies, startups, big companies, all trying to build a slightly better GPU, incrementally improving on this formula that we see. But to what end? When we started Cerebras, we felt that those kind of approaches were thinking too small. And we had a motto, which was go big or go home. And we literally did this, right? We built the biggest chip ever. And it wasn't easy. We had to invent wafer scale integration processes all the way down to the fab, inventing new architecture techniques. It wasn't easy. 5 years ago, we launched our first wafer scale size chip. And to this day, we are the only company that can build such a thing. Now, we're doing this not just because we want to post big numbers or some chest-beating exercise, but it turns out that when you make a chip this big, a lot of very hard problems become simpler. For example, on our chip, we have on-chip memory measured in gigabytes. That is now large enough to hold the entire model on-chip memory. And then we can add a ton of compute. And because this is all done on chip, this is a single chip after all, we have full memory bandwidth between the memory and the compute. With this technique, we have 7,000 times more memory bandwidth than a GPU. 7,000 times more memory bandwidth. It's mind-boggling. With that performance, memory, we completely remove the memory bandwidth bottleneck. So now let's see how this compares with a GPU. And to do that, let's use a performance graph that NVIDIA presented at their GTC keynote just a couple months ago. Now on this graph, the x-axis is inference speed, measured in tokens per second. This is what the user experiences. Now, they have also conveniently labeled that axis for us. To the right is faster response. To the right is also smarter AI because of inference-time compute. This is where GPUs are today, about 250 tokens per second. This is the H100 that probably many of us in this room are using every single day. And this is their next generation, about 600 tokens per second. Now, we have to keep in mind that this is NVIDIA's marketing performance numbers. They are going all out, pulling out all the stops. This is an NVL72 rack scale solution, right? 72 Blackwell next generation GPUs strapped together with thousands of cables going down to batch size of 2, FP4. I'm not even sure if model quality can be preserved in all cases in FP4, right? This is going all out. 600 tokens per second. So where is Cerebras? Well, we don't fit on this, so we have to zoom way, way out. All right? This is the current generation GPU. This is the next generation. And this is Cerebras. That is absolutely the right response, because Cerebras is 5 times faster than NVIDIA's flagship NVL72. This is a GPU that isn't even available to most of us yet. 5 times faster than the fastest next generation GPU. We call this GPU impossible because no number of GPUs can do this. But it's not just about speed, because as you remember, our inference scaling law states that faster inference equals higher intelligence. So instead of tokens per second, you can think of this graph as showing intelligence on scientific question answer. 10 points higher on GPQA. Or maybe better coding. 20 points higher on live code bench. Or smarter, more intelligent math reasoning. A whopping 40 points higher on the AIM math benchmark. This is universal. And just as they labeled on their graph, it's because faster response equals smarter AI. So what's the result? Well, imagine a reasoning model running on Cerebras. Just imagine what that would be like. That would give us reasoning in seconds, not minutes. And it would unlock a level of higher intelligence that is not possible on GPUs.